Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be looking at Unit number 13, Lesson number 5 on sample means. All right, this is going to be our first lesson on what is known as inferential statistics, and this is really cool. It'll also be our first lesson where we're doing some statistical simulation. Now, in order to really kind of launch us into this lesson, what I want to do is talk about the difference between the two major branches of statistics. So let's get into that on the first slide. All right, descriptive versus inferential statistics. See, the majority of the time that you've been working in statistics, you've worked in what's known as descriptive statistics. And these are measurements simply of how a data set looks, all right? And basically everything you've ever done, except for maybe a little bit of the work we've been doing lately, has been with descriptive statistics. So, when you calculate a mean or a media, I like that. How about a mean or a median? That's great. A mean or a median, or measures of dispersion like standard deviation, range, interquartile range, the general distribution, like whether you're talking about a histogram or a box plot or a dot plot. All of those are descriptive statistics. They take a set of data, perhaps that set is a sample, perhaps that set is an entire population, regardless, and it looks at the way that measurement, the way that data looks. How is it distributed? Now, on the other hand, the more, might I say, powerful branch of statistics is what is known as inferential statistics. And the idea here is that we use a sample to infer properties of a population. Now, I'm going to pause there for a moment. In almost all practical situations, it is impossible to get data on an entire population. Sometimes it is. But the vast majority of times, especially in science, it's not. If I'm trying to measure the effect of a particular, let's say, drug in terms of immunity to a disease, I can't take everybody out there who's going to get this drug and give it to them and see what happens. I have to take a sample of people, right? A sample of people. So where inferential statistics comes in is taking a sample, measuring that sample, and then trying to infer properties of a population from which that sample came by what the sample's characteristics are. And we do this by using probability and sampling variation, right? So probability, we just did a unit on that, and sampling variability to estimate how likely a sample is, that's the probability part, how likely a sample is given a population with certain parameters, all right? And today what we're going to really be doing is looking at how we can take a sample, look at its mean primarily, but it's also its standard deviation, but primarily look at its mean, and try to then say something about the population mean, which we will never know. We won't know the population mean, but try to say something or infer something about the population mean based on the sample mean. All right? That's inferential statistics. Let's jump into it. All right. Exercise number 1 says, say we are investigating the heights of 16-year-old American males. Say we know that the population mean height is 65.3 inches, with a standard deviation of 4.2 inches. Let's say we take a sample of 16-year-old American males. The sample size has a size of 30, or the sample has a size of 30. By the way, this is pretty important, sample size. When you're doing inferential statistics, the larger the sample you can get, the better. But at the bare minimum, you shoot for a sample size, I think, of 30. All right? Now, for some reason, we think we know that the population mean is this, and the population standard deviation is that. All right? Letter A says, will the mean height of the sample always be 65.3? Why or why not? Could it be significantly different? Pause the video now and think about this a little bit. All right. Well, what I hope is that you said no. Okay? In other words, because of sampling variability, the sample will almost never have the same mean. Will almost never have the same mean as the population. Right? It most likely won't have the same mean as if we did another sample, right? We saw that, I think, in the first lesson in statistics, is that we took a couple of very small samples and we got different sample means, right? Now, could it be significantly different? Yes, it could be, but it is unlikely. So there's the sort of terminology of probability. It is unlikely to be significantly different. Again, it could be, right? But it's unlikely to be. Okay, letter B. Will the standard deviation of the sample be 4.2 inches? Would you expect it to be more or less? Would you expect more or less variation in a sample versus a population? This is, again, an interesting set of questions. So pause the video and think about this some. Okay. So again, answering the first question, no, for the same reason, i.e. sampling variability. All right. Now, how about would you expect more or less? Well, generally, we expect less variation in the sample than the population, primarily because it's just smaller. It's just smaller. Now, don't get me wrong, again, due to sampling variability, you could grab a sample, and you could actually see more variability than in the population as measured by the standard deviation. But again, that would be pretty rare. Because we've got smaller samples, one would think that you would have less outliers in a sample than you would in the population. Almost all populations have outliers of one type or another. And in the sample, it's very likely that you are not going to get those outliers, which is going to cut down on your variability. All right, think about this a bit before we go on to the next page. All right, clearing this out. Okay. Now, on this page, we're going to run into the first time that we're going to do a statistical simulation. Statistical simulations are very, very important. They allow us to randomly simulate what it would be like to take samples. Now, what we've done is we've created a program called NormSamp that can be accessed both from the web, but also on the TI calculators. Now, I hope that you've actually downloaded this. And we're going to have to take this presentation and we're going to have to do it a little bit differently from now on. All right, in order to do the calculator simulation and show you how it's done, that takes a little bit of time. So I'm going to actually have to kind of pop out of the presentation I'm in to show you how to do it on the calculator. All right. Now, what this particular program does, NormSamp, is it allows us to create a normal population, a population with a normal distribution, with a mean of 65.3 and a standard deviation of 4.2, and then I can take samples of any size out of that. It's going to randomly grab a sample. So it's almost like the computer program is going to close its mind, take this normal distribution, and just grab a random sample of 30 out of it, and then it's going to calculate its mean and its standard deviation. And it's going to do it again and again. It's going to do another sample of 30, and then another sample of 30, etc. All right, we're going to do the simulation 200 times, but I'm going to actually break out of the presentation software I'm in right now. That means you get to see the background of my Macintosh, and I'm going to come into the calculator. All right, and I know this is a little bit weird, but it's the way I've got to do it. Due to the random nature of simulation, I can't like kind of pre-record the simulator multiple times. So let's go into our programs. It's right here. And I'm going to go down to normal sample. It ends up being option 2. And I'm going to just hit enter. All right, and it asks me for my mean. And my mean is 65.3. Enter. Standard deviation, 4.2. Enter. Sample size, we want a sample size of 30. And the number of samples, which is the number of simulations, 200. All right. Now this is where it gets kind of boring because the calculator needs some time. It needs time to like generate. Each one of these like things that it's generating isn't a single data point. It's a sample of 30. All right. So I don't want you to have to sit here for the next 5 or 10 minutes watching this thing blink away. What I'm going to do is I'm going to snap my fingers and I'm going to cut it so that it comes back to me right around when the thing is finishing up. Okay? All right, well, we're back, and it's just about done with the simulation. As you can see, we're almost up to 200. It gets to 200, and it takes a little bit because it's doing a little bit of math right now for us. There we go. And the program says sample means in L1 and sample standard deviations in L2. So what I'm going to do right now is I'm going to actually go in, I'm going to take a look at the data lists. All right. Now again, what I've got over here in L1 is in ascending order. These are all the means, all the sample means that came out for these various sample samples that we took. So what's great is that they're organized in ascending order. And I'm going to write these down just on a sheet of paper right now. The minimum that I have, let's round it maybe to the nearest tenth, was 63.6. That was my smallest mean. Now, one of the cool things you may not know about a data set, I don't really want to hit down 200 times. So if I go up and then hit up arrow one more time, I can get to the last element in my list. The largest mean, the maximum mean, was 67.1. So you do see quite a bit of variation in these sample means, right? And that's all due to sampling variability. The sample that we took that had the smallest mean was 63.6, and the one that had the largest was 67.1, which are both relatively close to 65.3, but not exactly the same. Now, this question also asks us for the mean of the means and for the standard deviation of the means, all right? So what I'm going to do is I'm actually going to go into Stat, and I'm going to go over to Calculate, and I'm going to do one variable stats on all those sample means. All right, now I'm going to delete that L2 out of my frequency list. All right. And I'm going to do one variable stats on those means. So the amazing thing is that the mean of my means, the mean of my means is 65.25. We'll leave it like that. And the standard deviation of my means, which I'm going to go with S sub x because it is a sample of all the standard deviations, I'm going to say is 0.73. 0.73. That would be the same if I took the population standard deviation as well. All right. Now that's enough. We can actually go back into our keynote presentation, I think. There we go. And now let's write some of this stuff down. All right. So the minimum sample mean was 63.6. Now when you do the simulation yourself, you're very likely to get different numbers. That's the randomness of a simulation. The mean of the means was 65.25, and the standard deviation was 0.73. Now, it says, how does the variability of the sample means compare to the variability of the population? Is it more or less? Well, before we even go on, I just want to point something out. Take a look at this. The mean of the means compared to the actual population mean is pretty much identical. Even though many of the means were very different from the population mean, The actual average of all those means, the mean of the means, was just about the same. But look at the variability in the means, right? What would you say about the variability in the means? That would be written like this. All right, that's, well, no, actually it'd be written with an S, my bad. What can you say about this versus this, right? And obviously what you can say is the variability in sample means is much less than the variability in the population. Now, I want you to keep in mind what we are not saying here. We are not saying that the variability of any given sample is much less than the variability of the population. We'll maybe take a look at that in just a bit. But the actual variability in the means was much, much less. In other words, the means, the sample means, are much closer to the population mean than the individual data points within the population are. All right? Now, letter E, we're going to have to pop back out in a second. So before we do that, maybe pause the video and write down anything on this sheet that you need to, because I'm going to erase it before I pop back out. Okay, I'm going to clear this out and pop back out of my keynote. All right. Letter E says, state the mean of the sample standard deviations. Well, again, if I go into stat and I go into edit, all right, here in L2 are all my sample standard deviations. By the way, notice my smallest one is 2.7. For my population, it was 4.2. And my largest one was 5.7. So we had some samples that had standard deviations larger than that of our population, and we had many that had sample standard deviations smaller than our population. But let's see what the mean is. Let's do stat, calculate, one variable statistics, but now I want L2 in there. And I'm going to write this down with a different pen. So now the mean of my standard deviations was 4.09. All right. I'm going to go back into my keynote. So it says state the mean of the sample standard deviations. All right. The mean of my S's was 4.09. How does it compare to the population standard deviation? Well, the population standard deviation was 4.2. And they're roughly the same. They're roughly the same, right? They're quite close. And what this does mean is it says, could you use the standard deviation of a sample to estimate the standard deviation of a population? And that means yes, you can use sample standard deviation. Now, again, I think we should note that there were some of those sample standard deviations that were lower than the population standard deviation, and there were some that were higher. But because the mean of the sample standard deviations was the standard deviation, or close to the standard deviation of the population, it means that it's an unbiased estimator, meaning that there's nothing about the sample standard deviation that should make you go, no, man, no, there's bias built into that. I shouldn't use that. All right. Anyhow, let me clear this out. Take a moment if you need to. and let's keep going. We're going to do some more simulation in a little bit, but let's take a look at exercise number 2, because this really starts to get into inferential statistics. It says Mr. Weiler took a sample of 30 16-year-old males, so the same deal as what we had before, and found the mean height of the sample to be 66.4 inches. So we took this sample, and it had a mean height of 66.4 inches. All right. Do you believe this sample came from this population? All right. Do we believe that this sample came from this population? Why or why not? Examine the results of your simulation. Quantify how likely this sample, or one greater, was to come from the population simulated. All right. So again, I'm going to clear this out. We're going to pop out for a moment, and we're going to look at our results. Okay. Let's go into Stat, and let's go into Edit. Let's find about where 66.4 lies. Now that's actually one of the higher ones, so let's look at it. Let's see, we're getting there. All right. There's the first one that's 66.4 or above. All right. Now what is that? That is the 190th one. So when we simulated this, from our population, I'm going to go back into Keynote. All right. The 66.4, I keep doing that. You can tell I haven't done this type of presentation before. All right, this was the 190th out of 200 simulations. All right, the 190th out of 200 simulations. That's 66.4 inches. All right, so that's actually, if you do 190 divided by 200, that puts it at the 95th percentile, or roughly 5% of the simulations had a mean equal to or greater than 66.4. So what does that really tell us? Well, what it really tells us is that in all likelihood, this sample did not come from this population. Now you might say, oh, well, but there's a chance it did. There were some of the simulations which gave us a mean that high. True, but only 5% of them. So there's actually a 95% chance, if you want to think about it that way. You can think about it as really that there's a 95% chance that this sample actually came from a population with a higher mean than the one that we simulated, right? Because so very few of the samples that we simulated had a mean this high. We have quite a bit of confidence that the mean that we took this sample, or the population we took this sample from, has a mean that's higher than the one that we were simulating. All right, that's a very important idea. So think about that some before we clear out this sheet and move on. Okay, I'm doing it. Let's keep going. All right, another simulation. A sample of 50 ripe oranges were taken from a large orchard in order to estimate the mean weight of a ripe orange. Okay, great. The sample mean was 212 grams, and the standard deviation was 34 grams. Letter A, why does it seem reasonable to use the sample standard deviation as an estimate of the population standard deviation? See exercise 1E. Well, again, this is very, very subtle, but the sample standard deviations are unbiased estimators. Due to their mean being equal to the population standard deviation. All right, so we're going to actually use that as our standard deviation. Now letter B says run a simulation using the 212 as the population mean, even though it's the sample mean, and use 34 as the population standard deviation, even though it's the sample standard deviation. State the 5th percentile sample mean and the 95th percentile sample mean. All right. Well, since I have to pop back out and that text would hang out on the screen, I'm going to erase it. So take a moment to write down your answer to letter A if you need to. Okay, I'm going to get rid of it. And let's pop out and run this simulation. Okay. I'm going to move this a little bit to this direction so we can see letter B a bit better. All right, let's go into our program. Let's go down to normal sample. Let's put in 212 as our mean. Put in 34 as our standard deviation. Now, what should our sample size be? Well, because we made an original sample of 50, we should continue to have a sample size of 50. Now the number of samples, the number of simulations. Well, the more simulations, honestly, the better. It'd be good to do 1,000 simulations right now. But what I'm going to do is simply 100. It's going to make it very easy then to come up with the 5th percentile sample mean, because it's going to be the 5th one in the list, and the 95th percentile sample mean, because it's going to be the 95th one in the list. So let's do some simulation. Now, just like before, I don't want to waste your time and have you sit here, so I'm going to do a little cutting of the video. So if there's a little herky-jerky with my head and stuff like that, please excuse me. It's to save you some time, okay? So I'll come back to you when we're a little bit farther in the simulation. All right. Well, as you can see, the simulation is finishing up, right? It's getting up to our 100th simulation. It's just about done. And there we go. All right, so we're back to sample means being an L1, sample standard deviations being an L2. We're not going to really need the sample standard deviations anymore, but let's pop into our stat. Let's go into our edit, and let's come up with that 5th percentile value. It's going to be pretty simple. We just have to go down to the 5th value. There it is. And again, I'm going to write these things down on a sheet of paper. My 5th percentile value is 205.438. Now to get to our 95th, it's easiest to go up and then scroll back to here. Here we go. 96, 95, and our 95th is 220.102. So again, understand this. If we had a population with a mean of, what was our mean? A mean of 212 and a standard deviation of 34, we would expect a sample of size 50 to show up at 205.438, 5% or less of the time, and we'd expect a mean of 220.102 to show up 5%, that mean or greater to show up only 5% of the time. All right, so let's pop back into the presentation just to make sure you kind of got this. All right, our 5th percentile mean would be, the next time I'm not going to do that, would be 205.438, and our 95th percentile, 220.102. So there's quite a bit of variation, right? If I had a population with this mean and this standard deviation. Now what's weird is I don't have a population with that mean and that standard deviation. That was a sample that I took. But letter C says, now try your simulation again, but use the 5th percentile mean, this thing, the 205.438, as the population mean. So I'm going to do exactly the same thing, but I'm going to put that in as my mean, and I want to know where my 212 lies. Okay, I want to see how close that lies to, or where that lies in my list. Okay, and again, since I have to pop out, all of this text is going to kind of stay on the screen. So I got to clear it out. I'll write those values back in there again, but we're doing another simulation. Okay, we're going to go into stat. No, we're going to go into program, down to normal sample. All right. This time I'm putting in a mean of 205.438. And I'm going to put in a standard deviation of 34. I'm going to put in a sample size of 50. And I'm going to put in 100 samples. And again, just like before, I'm not going to make you sit here forever and wait. That would take up too much time and it would make the video like 60 minutes long. And it's long enough already. So let me pause now and cut right to the end. All right, well, we're back to it. So the simulation is just about finishing up. It's getting there, 97, 98, etc. 99, 100. All right, so remember what we just did. We just ran a simulation, strangely enough, found the 5th percentile, and we got 205.438. Then we used that as our mean. And what I'm now curious about is where my 212 lies. Now, it's actually going to be one of the largest ones. So let me go down to here. I'm looking for that 212. Well, there's 211.6. There's 212. So it's around the 93rd one. It's around the 93rd. All right. Now, I'm not going to write that down. I'm not going to pop back in. What I'm going to do is I'm going to do letter D right away. So letter D says, now try your simulation again, but use the 95th percentile sample mean as the population mean. Where does the 212 lie? Now, by the way, just on that last one, notice that 212 lied pretty close to the 95th percentile. Now, it sort of makes sense. If the 212, if using the 212 gives us the 205.4 as the 5th percentile, then using the 2.05 gives us the 212 as the 95th percentile. And watch what happens here too. Same idea. Let's go back into our program. Let's go down into our normal sample. Enter. Now what I'm going to use as my mean is I'm going to use the 220.102, which was my 95th percentile mean when I used the 212. I'm going to continue to use the 34, no reason to use anything else. I'm going to continue to use a sample size of 50. And I'm going to continue to use 100 samples. All right. And as before, what I'm going to do is I'm going to pause the video, or not pause the video, but I'm going to cut the video so you don't have to watch this entire simulation. All right, so we're back. The simulation is finishing up. This will be our last one of the lesson. I know that this takes quite a bit of time, but we'll make our point in just a moment. All right, now what did we do? We took that 95th percentile and we used it as a mean. All right, and what we want to do again is see where our sample mean of 212 lies. Now this time 212 is on the smaller side of things. Where is our, there it is. All right, so it's around the 6th percentile. All right, so around the 6th. That's about as good as we're going to do. So let's pop back in to here, And I'm going to fill quite a bit of this out. I'm going to leave letter A because it took us a little while. So let's summarize what we had. When we ran a simulation where we said that the mean, hey, I remember this time, was 212 and the standard deviation was 34, we found that the 5th percentile was, let's say, 205.4. All right, and our 95th percentile was 220.1. Then when we used the 205 as our mean, we found that the 212 was roughly at the 90, well, what did we have? We had the 93rd percentile, but that was approximately the 95th percentile. And we even came closer here when we used the 220.102. What we found was that the 212 was at roughly the 6th percentile. Now, what's the point here? The point is that what both C and D tell us is that by using the 5th and the 95th percentile, specifically these two values, based on our original sample, we've roughly found the lowest population mean, that's this one, the lowest population mean, and the highest population mean through simulation that could have resulted in our sample mean 90% of the time. And it's 90% because we're between 5% and 95%. We're between 5% and 95%. So that's the 90% of the time. 90% of the time, a population mean is going to fall between these two numbers if it produces this as a sample. If it produces that as the sample, that means that 90% of the time the population mean must be somewhere between that. And what that allows us to do is set up what's known as the 90% confidence interval. All right, we can literally write down that we are 90% confident that our population mean lies somewhere between these two. All right, and it's funny, of course, because I've done these things many, many times, and so I've found different things as I've gone along, but I'm 90% confident that my population mean lies between 205.4 and 220.1 using simulation. Higher level statistics gets into all sorts of different techniques where you come up with confidence intervals, but for me, I have 90% confidence through simulation that my population mean lies somewhere in between those two numbers. That's a pretty broad range, but I'm now able to infer something, right? I'm able to infer something about the population from results that I got from a sample, right? I can't say for certain at all what my population mean is, but I can say with 90% confidence that it lies somewhere between 205.4 and 220.1. All right, we'll pause the video and write down anything you need to. Okay, let's clear out this text. All right, the challenge of inferential statistics is that when we have large populations out there and we can't sample the entire population, then we've got to be able to take a sample, calculate a mean, and then say, well, wait a second. You know, that mean is not necessarily going to be the population mean, but can I come up with a confidence interval? Can I come up with an interval that says, hey, based on this sample mean and its standard deviation, and using simulation, can I now say, well, you know, I simulated 100 times. I'll go to that 5th one in the list and the 95th one in the list, write those down, and that then becomes an interval that I am 90% confident that my population mean actually falls between. All right? We're going to do more inferential statistics in the next 2 lessons, and you'll hopefully get a sense for where other statistical simulation comes in. All right. For now, I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.